kind of setting the foundation, we remember water, molecule. Oh, that's going to freak us out, isn't it? We can see that with its bent shape, when one water molecule collides with a second water molecule, we have the potential to cleave off, cut off, chop off a hydrogen ion, and this very positive region actually gets donated over to this very negative region in terms of a proton transfer. Water will do this. It will autoionize. When one water molecule collides with just the right orientation in space and just enough kinetic energy to get over the energy barrier called the activation energy, we see a proton transfer where one water molecule loses a proton and the other will gain it. The proton is attracted to the negative region of the second oxygen. So one water molecule colliding to the next will produce a hydronium ion and a hydroxide ion concentration. And those are the two things that we begin to measure in terms of, is the solution acidic or is it basic? Acidic solutions we know have more hydronium ion compared to hydroxide, and basic solutions are the opposite. They would have more hydroxide as compared to hydronium. No individual molecule remains ionized for very long. This is a very quick and not very frequent activity, but when they happen, it occurs in both directions. So think of this as a dynamic equilibrium where once in a great while, 2 out of every billion molecules are actually successful. That's like winning the lottery, isn't it? 2 out of a billion people might win the lottery. Why couldn't it be me? But anyway, 2 out of a billion people, 2 out of a billion molecules might actually ionize. If water bombards with itself and sets up an equilibrium between the acid ion and the hydroxide ion, we could write what's called an equilibrium expression. Products over reactants, where pure solids or pure liquids simply drop out of our expression. Well, water is a pure liquid, so the only thing that's left to write about in terms of equilibrium is the concentration of the hydronium ion times the concentration of the hydroxide ion. Products over reactants, but pure liquids drop out, and we see what's called the ion product constant for water. Last chapter we had Kc for concentration, Kp's for pressure. Here's a new critter called Kw, standing for the ion product constant for water. And constant does indeed mean the same. It's a value of 1 times 10 to the negative 14th molar units. It is equal to the concentrations of the acid ion times the concentration of the base ion. Whatever I do to one, the other adjusts to keep the constant the same. In every aqueous solution, if it's pure water, these two values are indeed the same, 1 times 10 to the negative 7th power. And we can start to see the establishment of our pH scale, where 7, right smack in the middle, represents an equal amount of our acid-base ions. pH of 7 is called neutral. The pH at the top of our scale is 14. The top of our scale represents the ion product constant to the negative 14th power. If we have a solution where we have more acid ion, the solution ends up with low pHs, we call it acidic. And if the solution has a greater concentration of the base ion, the solution ends up with a high pH, or it would be called an alkaline solution. So no matter what I do to the concentration, the other adjusts to keep the Kw a constant. And all we're going to be asked to do in our series of problems is to calculate one variable or the other, the hydrogen or the hydroxide ion. If we look at calculating the concentration of hydrogen and hydroxide, let's call the hydrogen value X. The hydroxide ion could also be X, knowing that we're going to create equal amounts. Now I know hydrogen ion to be equivalent as hydronium. They're indeed one and the same. The constant we know to be 1 times 10 to the negative 14th. That's equal to the hydrogen ion, let's call it X, times hydroxide ion, let's call it X, or X squared. pulling out for x, what we're really solving for is indeed the concentration of hydrogen and hydroxide, and we can see that it comes out to be 1 times 10 to the negative 7th molar units, just adding exponents there. So the 7 gives us the value when they are indeed exactly the same quantity. What if they're not exactly the same and we start asking ourselves, does the solution have more hydrogen for acidic? Is it spot on even for neutral? Or indeed, are they have more basic ions? And really, when we solve for 1, we use the ion product constant, 1 times 10 to the negative 14th, is equal to the hydrogen ion, given as 4 times 10 to the negative 9th. What would the other concentration, the missing guy, which in this case would be hydroxide? Kw is a constant, the ion product constant for water. Given 1 ion, we can do a divide by problem and pull out the next. So on our calculator, we'd hit 1e negative 14 divided by the provided hydrogen ion, 4e negative 9. And I find a value of 2.5 times 10 to the negative 6. When I compare, and that's hydroxide, if I compare the magnitude of the exponent, a negative 6th power is actually a larger number than a negative 9 power. So in this particular example, hydroxide is in a greater amount as compared to hydrogen ion, and so therefore we would call this solution acidic. Oops, I'm sorry, basic. Got to scribble on my notepad. Hydroxide is greater concentration than hydrogen ion. It's a basic solution. In our next example, hydroxide is provided for us. Kw is still a constant, 1 times 10 to the negative 14th. The hydrogen ion is what we're looking for, given the other value of hydroxide, 1 times 10 to the negative 7th. This one should look familiar. We just did it right up above. Hitting the ion product constant, 1 times 10 to the negative 14th, divide by the given value of hydroxide, we get the same number, 1 times 10 to the negative 7th. The power of 10s show us these are indeed the same. We can start to see the logarithmic foundation of a pH scale. So this solution must be neutral. The last example provides us hydroxide ion again. The ion product constant given as 1 times 10 to the negative 14th. Let's pull out hydrogen ion and compare it to the provided hydroxide. The ion product constant of water, 1e negative 14, divided by the provided hydroxide value is 7 times 10 to the negative 13. I found 0.041, which tells us hydrogen ion is significantly larger than hydroxide, giving us an acidic solution. When we consider problems, we're saying that they assume at 25 degrees Celsius. If you ever be on YouTube. That's you, Kyle. So I'll finish up. I know the bell's going to ring, but I can at least get this far and set up the ion product constant for water divided by the other ion concentration. It'll be a very easy assignment tonight, just pulling out the other concentration. That's the next step of the lesson. I'm not asking you to negative log and find pHs. We're going up to section 16.4. Alrighty, and I'll edit that out, just trust me.